So you should now see my screen with DSAT version 4.8.2. Can you confirm?
Yes.
Okay. Already. So when you open DSAT, this is what the system will look like. On the left, you have tools, which I discussed in my previous presentation, that allows you to prepare the data. So we have one for crop management, we have one for soil data, and we have one for weather data. Then what is the core part is what we, in this center panel right here, where we talk about applications and when we talk about crops. So crops are broken down by different types of crops. So hopefully most of you are familiar with that. So we have cereal crops, we have fiber, that includes cotton, we have forages, so these are mainly the grasses. We have legumes, such as soybean, peanut, cowpea, chickpea. We have all crops, such as sunflower. We have root crops, such as cassava and potato, sugar, sugarcane, etc. So if you click on cereals, you now will see the list of current crops that we can work with in DSAT. So we have barley, which probably not very commonly grown in West Africa. We have chia, maize is commonly grown in the area. We have pearl millet, we have sorghum, we have rice, we have teff. I don't think you have teff, it's mainly Ethiopia, and we have wheat. So when we click on maize, you see now here on the right a list of experiments. So these are all experiments that have been conducted under real conditions in different parts of the globe. So for instance, the first one, BRPI, I think is actually Brazil. The next one is also Brazil. We have one FLSC, which is conducted in the United States. We have one here from Ghana, from WA. We have from Hawaii. We have data here from Iowa. So depending on the crop, it varies. We have some crops for which we only have one experimental data set. In this case, for maize, we have 12 different experimental data sets. So many of these are older, but again, these are very good data sets where we have the daily weather data, we have crop management, and we have some observations. So the observations are really key to what we're trying to do. So as an example, I want to show you the maize model. So if I click on UFGA 8201.mzx, you see here on the panel below 6 treatments. So this was an experiment conducted at the University of Florida. So UF is University of Florida. GA stands for Gainesville. Then we have the number 82. So we use a 2-digit year convention here. So this is actually 1982. I realize again, this is old. It's a very good data set. So we have 2 factors. One is water and the other one is nitrogen. So for water, we have rain-fed, we have irrigated, and we have what we call vegetative stress. For nitrogen, we have low nitrogen and high nitrogen. So again, we have all the data available. So I've selected this experiment. Now here on the right top, we have something we call run. So if we click on run the model, it should go quite quickly. So right here, I simulated 6 treatment of 1 experiment on my computer. And Vaktam, can you confirm that my information simulation are completed shows as well?
Yes, we can see it.
Okay, good. So again, to summarize from previous presentations, this is daily time step, in some cases sub-hourly time step. So this goes very, very, very fast. So then once we run the simulation, so again, the model you've never seen is in the background. So this is the same cropping system model we discussed previously. So now we can click on analysis and we have a whole set of outputs. But these are very cryptic. It gets a little bit of getting used to. But in many cases, you can more or less decipher what things mean. So the one I want to start with is called plan_grow.out. So this is time series data, and I will show you in a minute what it means. There's some of the detailed information related to plan growth. So we click on plot here on the right. It actually starts a new graphics program. So can you see Gbuild, Doctor? Doctor?
Yes, we can see it. Sorry.
Okay, I just want to be sure that. Okay, so this is a graphics program. So there's a new separate analysis program within DSAT that we have selected. On the left, you see here a set of variables that relate to plant growth. So you see leaf weight, stem weight, grain weight, above ground weight, harvest index, etc. On the right, you see the 6 treatments we have simulated. So we have rain-fed low nitrogen, rain-fed high nitrogen, all the way irrigated low nitrogen, irrigated high nitrogen. Now on the left here, you also see we have variables that are in bold and variables that are regular. So variables in bold means that we have some type of observation that we can use to compare model simulations with the observed data. So let's look at tops weight. So tops weight is total above ground biomass, leaf stems, including grain weight. We're going to look at all the simulations, all the treatments, click on next. And now we get this graph. So similar to what I showed you in my earlier slide, the lines correspond to simulated and the symbols correspond to observed. Now, in general, we can see that the model does do a fairly good job in simulating high water, high nitrogen, which is this black line, versus rain-fed and low nitrogen shown here in the bottom of the graph. Now you might say, okay, this is great, but this is visual. So we also have a statistic option shown here on the right. So if I click on statistic, a new box opens up, which shows for each individual treatment and variable the statistics. Now, the one we really like to work with is something called the D-statistic, which is good for time series analysis, where a value of 0 means very poor performance and a value of 1 means perfect performance. So we can see here that for the various 6 treatments, we have a value as high as 0.996 for run 4, and a value as low 0.984 for run number 2. So we're very good statistics when we look at these time series simulations. So then we can go back and say, okay, what about grain weight? We're really more interested in grain weight and tops weight. So I unselected tops weight, I selected grain weight. And now we can see again the grain weight, and we know that for maize, grain filling start much later than, of course, above ground biomass, shown here somewhat around 90 days after planting. And again, we have the high water, high nitrogen treatment shown here on the top, the black line, and the low nitrogen, low water rain-fed treatment shown here on the bottom. And again, we can look at the statistic. And we get fairly high D statistics again, slightly less than above ground biomass, but it's still very reasonable. Run 6, 0.993, and looks like run 1, 0.956. So we have again very good statistics, and we look at these simulations. So and some other variables that were predicted here as well. So there's a whole set of traits that the model predicts just purely associated with above ground biomass. So I can close this, and I can look at some other variables. So for instance, I might be interested to see, okay, what were the weather conditions during this experiment? So we actually Although we read it in as input, we write it back out as daily weather data as well. So we can click on plot, weather.out. Oops. My graphic disappeared. Here we go. So we can look at the maximum minimum temperature. But this is the daily data maximum minimum temperature for this particular environment. Or we can look at precipitation millimeters per day. We can look at CO2 concentration. We can look at solar radiation, etc. So there are many things we can plot. And I also mentioned that the model can deal with environmental impact and resource use. So one output is sol watt, relates to the sol water balance. The other one is sol nitrogen, so the sol Ni out. So I can actually select two output files. So I can look at all treatments. So here we're looking at sol nitrogen. So the question could be how much nitrogen is actually leached to the groundwater. So we have cumulative and leached shown here. So this is not so good. So some of the high nitrogen treatments, we lose about 120 to 130 kgs of nitrogen back to the groundwater. So again, if policymakers are worried about pollution of the environment, these could be fairly important outputs of the model. Or we can look at how much water is being used. So switch from sol nitrogen to sol water, and we can look at cumulative effective irrigation that was applied. So select cumulative effective irrigation. I look at the 6 treatments. And now we only have 3 lines because we only had 3 levels. So for the low nitrogen, high water, we see 250 millimeters. We see this one here about 200 millimeters. And for the rain-fed treatment, we only applied water at startup. So we have maybe about 10 millimeters and we don't irrigate any further. So again, this allows us to look at resource use. So not everything is about yield, but also how much water would be required to grow a crop we have to irrigate. We have some additional outputs we can look at. We have something called overview.out. This is something that cannot be plotted, but it can be viewed. This is very cryptic, but I can slowly guide you through one of the overviews, because this actually summarizes all the simulations. So this is what we call run 1. Shows the model version we use, 4.8.2.006. We're simulating treatment 1, rain-fed low nitrogen. The experiment was conducted at the University of Florida in Gainesville in 1982. This is maize. The version of the model we're using is series maize. Then we find more information here. We have the definition of the cultivar we're using, the Curdy 84AA. We started simulation on February 25th. We plant on February 26th. Plant spacing 7.2, density 7.2, row spacing 61 centimeters. Gives us some generic information about the soil, millhopper fine sand, and the initial conditions. As I mentioned earlier, based on one of the questions, initial conditions, boundary conditions are very important. So we assume that the total amount of 161 millimeters of water was available in the profile when we started our simulation, 2.5 kilograms of nitrogen in the form of nitrate, and 12.9 kilograms for ammonia. Irrigation only once, 30 millimeters. This is the rain-fed conditions. And we're only applying 160 kgs of nitrogen. So this is low nitrogen, although maybe for your conditions still relatively high, but not for Florida, in 3 applications. We're not applying manure, except we have some initial residue present. Environmental modifications we're ignoring. And then in the model, unrelated to the management, we can manipulate some of the processes. So I mentioned earlier nitrogen fixation. So we wouldn't expect that the series maze is fixing nitrogen, so we set it to no. We're very interested in the water and nitrogen balance. So we're simulating a water balance and a nitrogen balance. So we set it to yes, because it's irrigated, nitrogen fertilizer. We're not doing phosphorus in this case, we're ignoring pests, and then some other switches as well. With respect to CO2, this is also extremely important because we know that as of today, we're probably close to 410 parts per million, and CO2 has a significant impact on crop growth, and especially yield. So we have an external input file based on CO2 conditions that are measured at Mauna Loa. And we use that to set the CO2 conditions for this actual experiment. So this was conducted in 1982. So the model reads that input file, it looks for 1982, and finds in the input file that the CO2 is 341 parts per million. So comparing for an experiment conducted in 1982 versus 2024, there will be significant difference in CO2. Then I mentioned that the model uses a one-dimensional profile, so that's shown here. We use different soil layers from 0 to 5, 5 to 15, 15 to 30, 30 to 45, all the way to 180 centimeters. We have 3 critical inputs. So it is a simplified soil water balance. So we lose a lower limit, which is the equivalent of a permanent wilting point. We have a drained upper limit, which is equivalent to fill capacity, and a saturated soil water content. So if you have soil texture for your soil, you actually have pedo transfer functions that allows you to calculate the values for these particular parameters. And then we calculate extractable water, which is the difference between the lower limit and the drained upper limit. And we also define then the initial soil moisture, as I mentioned earlier. So these are all inputs, either through the soil profile or through the crop management section input. Then we also have these cultivar coefficients I also referred to earlier. So this is a variety called McCurdy 84AA. So we defined these cultivar coefficients. P defines phenology, P1, P2, P5. G defines growth, G2 and G3. Unfortunately, I don't really have much time to go into detail and then explain these. So once we defined all the inputs, we conduct the simulations. And right here, you see a summary of the key growth stages, starting with start of simulation, sowing, germination, emergence, and juvenile floral initiation, 75% silking, beginning rainfall all the way to maturity and harvest. Just the dates this occurred. So this is simulated, biomass simulated, LAI simulated, leaf number simulated, total nitrogen simulated, and then we have some stress factors. So the model uses a relative stress function where 0 is no stress and 1 is full stress. But this is a grain-fed treatment, so we can see somewhere at beginning grain filling a very high stress level at 0.78. So this affects grain filling, and this affects, of course, then yield. This is low nitrogen, so here 0.62, fairly high nitrogen stress during floral initiation, which will affect LAI, which will affect photosynthesis. And finally, we have a table here where we compare simulated with observed. This is mainly observations related to phenology. So we have Anphesis Day, We have physiological maturity day. We see the model predicted 76 days after planting, measured 75, maturity 128, 128. For yield, we're slightly under predicting here, so 2143 simulated, while we measure 2929. Total above ground biomass, we slightly over predict 6460 versus 5532. We had a question about quality. So in this case, we predict grain nitrogen, so grain at maturity. We simulate 1.7 and we observed 1.8. So this is treatment 1, rain-fed low nitrogen. So we repeat this for rain-fed high nitrogen. Then we have irrigated low nitrogen and we have irrigated high nitrogen. So let's look here at the yield levels. So we see from phenology, not much difference between the various treatment. We can see for yield, that's significantly higher. So yield at harvest maturity is 11,859, simulated, very close to observed, 11,881. Tops weight, 22,526, slightly higher than measured, 22,000. Grain at maturity is actually slightly less because we got a dilution factor. Simulated 1.5 and measured 1.6. The other part I forgot to mention, many people are interested in what's happening during the particular phases of the plant. So right here, we define 5 phases for maize. And during those phases, we calculate the average maximum temperature, minimum temperature, mean temperature. We look at photoperiod, so that's day length, average solar radiation per day, CO2 concentration, rain, ET. Then there was a question about stresses. So actually calculate the number of days that the maximum temperature is above 30 degrees, 32 degrees Celsius, and 34 degrees Celsius. Number of rain days, and then some of these stress factors for water, for nitrogen, etc. We also calculate resource productivity. So depending on what you're interested in, if you're interested in rainfall only, in irrigation, if you look at dry matter productivity, if you look at yield productivity, we calculate all of those as well with respect to water. And then we also do the same with respect to nitrogen applied for dry matter, for yield, and also nitrogen uptake applied versus, for dry matter productivity and for yield. So this is in a nutshell, the very quickly an analysis of the simulation. So let me stop here and entertain any questions you might have so far.
Hello, Prof. Can I go?
Yes, sir. Finding data. So depending on your background, we recommend that if you personally don't have access to experimental data, that you try to work with maybe a colleague who might have experimental data that you can use then for model calibration. What I normally would recommend people start with actually is check the literature with respect to papers. In my presentation, I know it went very fast, but I showed you that for South Asia and China, there are hundreds of papers that have been published already on DSSAT. So some of these papers include some of these cultivar coefficients that could be challenging for you to obtain. I think you mentioned you're based in South Africa. But we have several users in South Africa that have used DSSAT and actually have published on DSSAT. So if you don't have access to the data, that is where I would start and find other papers of colleagues who've actually calibrated and evaluated a model, and then use their genetic coefficients. That would be my first step. My second step would be then, if that's not possible, than to find papers that have been published on experimental data that can be used for model calibration and evaluation. That could be more challenging because people might not have provided daily weather data, probably highly unlikely. They might not have provided the soil data. So in that case, you might have to contact them, or if the latitude or longitude is available, go to another resource to obtain that information. If that doesn't exist, the last resource we sometimes recommend you can use is data from variety trials. I showed you the example from Georgia, but I know across the world, breeders are conducting variety trials, and they normally publish the data in reports. These are not necessarily scientific papers, but the information they publish can be very valuable for you to calibrate the model. I know some of you might be associated with the CGIR system, and they have breeders that work in South Africa, West Africa, and they also conduct variety trials, so that information can also be used to determine those cultivar coefficients. I mean, for me, really, to try to cover data inputs, model calibration, and evaluation in 30 minutes is impossible, because we spent 4 days during a regular DSAT workshop discussing that in detail. So, I mean, I understand your challenges, but I gave you some very broad advice on the steps to take, but it takes more hands-on experience and showing how we approach it to really dive into it.
Okay, no, thanks a lot, Prof. Maybe my other question that I have is, in terms of the results, like the tops weight at maturity, it's based on what? Is it a farm level, or what is it calculated from?
So the yield I showed you here is from experiments. So, and then the yield we use in the model currently would be dry yield. So, I mean, all the experiments we have in DSAT are not on farm, not from farmers' fields. We recommend that model calibration and evaluation is done, first of all, with experimental data from managed experiment, not on farmers' field. I mean, we realize that in farmers' fields, many crops are not managed optimally because inputs are lacking, there might be stresses, etc. So these are from relatively well-managed trials.
Okay. So what is the recommended maybe period for observed data for calibration?
So the minimum of the minimum would be just having one experiment. But the problem is, if you have one experiment, if you work with values for multiple coefficients, you can different values for the same coefficients can result in the same yield prediction.
Yes.
So we recommend that maybe you use data from 2 environments, preferably 2 different years, to do calibration, and that will result in values that are more robust for those coefficients. Could also be different planting dates, but they shouldn't be too close together. It's really important that the crop is exposed to different temperature, maybe different photoperiod, maybe different solar radiation.
Okay, no. I think maybe, yeah, I don't know, because I wish you could have maybe, if there's a chance to share maybe some screenshots of how. I'm interested in checking how the input files are set up to
Okay, yeah,
run
I mean,
the-
unfortunately, I think what I recommend is, you're really interested in DSAT. We have YouTube videos on the DSAT portal. I suggest you start there, because we have each of the input files. We have a YouTube video.
Okay, no problem. Thanks, Prof.
So now we're starting to run over time. So are there any other pressing questions?